All right. So we're setting the numerator equal to 0. We can divide both sides by a -6. It's gone, so we just have -x minus 3 equals 0. Add the 3 to the other side and divide by a negative, and we get x equals -3. And then we ask ourselves, is that a critical value? To answer yourself, you come back and look at this domain here. The domain is everything except +3. So -3 is a critical value, yes. So beside critical values over here, I can go ahead and put x equals -3. So this gave me one critical value. Now I need to see where the derivative does not exist. For that one, I set the denominator equal to 0. So my denominator, I just need what's in parentheses there. X minus 3 equals 0. And I get x equals 3. And then I ask myself, is that a critical value? And to answer myself, I look at the domain and say, no, it's not a critical value because 3 is not in the domain. So this is not a critical value. However, it's still important enough to go on a number line. So I'm going to put out a number line and I'm going to put -3 and 3. But underneath 3, I'm going to make myself a note that this is not a critical value. Otherwise, I tend to get confused as the problem goes on, and it may look like a max or min, and I don't want to accidentally say it is when it's not. Picking numbers to the left and right, I'm going to test all of these numbers in the first derivative. And Danny, what's the only thing we care about the first derivative? Positive, negative, that's all we care. So I have my first derivative right up here. I'm going to use my calculator and my table for this. I'm going to go to y equals. And then if you've got the nice new calculator, you can do alpha y equals and then choose n over d, which will do numerator over denominator. So you don't have to worry about parentheses. If you've got an old school calculator like me, we're going to be putting parentheses here. I mean, an old school, whatever. I don't know what I'm saying. And then some people in my earlier class had forgotten, or they cleared their calculator and they weren't able to ask their table stuff. It's okay if you're not able to ask it and you're testing integers, but if you're testing fractions, you need to be able to ask it. So make sure when you go to second window, underneath independent, it says ask right there. All right, and I'll type in -4, 0, 4. And all I care about is positives and negatives. So I got a positive, a negative, and a positive. That means I was increasing, decreasing, increasing. So for increasing, I can put my interval as -infinity to -3. Just pay attention to each homework problem because some of them say use a comma, some of them might say use a union sign. Just pay attention here. And then I'm going to go from 3 to infinity. Decreasing from -3 to 3. For a maximum, it looks like we go up and then down around -3. So we're going to have a maximum at -3 something. How do we find the y value for that?
You plug in the x value into the original.
Yes, plug it back into the original up here. And when you do that, I want to say you get half, 1/2. And then for a minimum, this is where you want to make sure you wrote not a critical value because it looks like a minimum, but it's not because it's not a critical value. So there is none for minimum. Okay, any questions so far? We're doing okay? Yeah. So now these next three are going to be answered using the second derivative, and then we're going to put it all together with a graph. So using the second derivative, I'm going to take the derivative of my first derivative, but I'm going to first rewrite my first derivative because I don't like the -6 just sticking out there. I'm going to distribute it through. So my first derivative is going to be -6 times -x is 6x. -6 times -3 is plus 18 over x minus 3 cubed. All right. And then using the quotient rule, low d high minus high d low. I'm going to find the second derivative. So low, I'll just write it down. D high, derivative of the high is 6 minus high, just write it down. D low, I have a bunch of junk to the third power. Derivative is going to be 3 junk to the second power. Copy paste the junk times the derivative of the junk, which would be times 1, over the square of what's below. But what's below is currently to the third power. So if I square a third power, power to a power you multiply. So that would be 6. Simplifying, there's my subtraction sign. On the left, I have a 6, and on the right, I have a 3. So the most I could take out of this is a 3. And then I can take out 2 of these ugly terms. It's going to leave me with, on the left side, I took out a 3, so it leaves me with a 2. And I took out 2 of those, so it leaves me with 1 of those. On the right side, I took out a 3 and I took out this whole term. So it leaves me with 6x plus 18, which I'm going to write in parentheses. Why is that important? Yes, got to distribute that negative sign or it changes everything. All right, now that this is being multiplied, I can cancel those 2 with 2 of those. Here I'm going to distribute, and I get 2x minus 6, and I'll distribute here also, minus 6x minus 18. So I have 3 times 2x minus 6x is negative 4x. Negative 6 minus 18 is negative 24. And then that's over x minus 3 to the 4th. Technically, I could still take out a 4 or a negative 4, but it's not necessary for what we're about to do. So I'll just leave that. And I'm looking at 2 things. I want to know, where does the second derivative equal 0 and where does the second derivative not exist? The second derivative is going to equal 0 wherever the numerator equals 0. So I'll set this numerator equal to 0. Divide both sides by 3, and I just get negative 4x minus 24 equals 0. If I add 24 to the other side, and then divide by negative 4, I get x equals negative 6. And then I ask myself, is this a possible inflection point? So to answer myself, I got to go back up and check out my domain. My domain is everything except 3. So yes, this is a possible inflection point. Uh-huh.
I have a question. How did you solve it down back there? So the 3 is gone because 3 can't equal 0.
Because I can divide both sides by 3 right here.
Oh, okay, right. And then you
And
just.
then I added that over.
Oh, okay, oh my gosh, yeah.
No, you're good, you're good.
Yeah, thank you.
All right. The second derivative does not exist wherever the denominator equals 0. So I'm going to set the denominator, just what's under parentheses, equal to 0, and I get x equals 3. And then I ask myself if that is a possible inflection point, and it is not, because it is not in the domain. Our domain said everything except 3. So this is not an inflection point. But it's still important, and so I'm going to put it on my number line. And I'm going to scroll up a little bit because I'm running out of real estate to write, as you probably are too, but erasing a bit here. Any questions while I'm erasing some stuff?
I have a question.
Okay.
For the holes, I know this problem doesn't have any, but say it did have one. Do we have to put it on each number line that we make, like the one for the first derivative and
Yes.
second derivative?
Yes.
Okay.
Because you cannot increase or decrease or concave up or concave down through a hole. So holes always go on the number line.
Okay, thank you.
Uh-huh. All right, so I'm going to make my number line here. And we have -6, which is a possible inflection point. And we have 3, which underneath I'm going to write not an inflection point. Then picking numbers to the left and right of each, I'll pick -7, 0, 4. And I want to test all of these in the second derivative. The only thing I care about in the second derivative is whether it's positive or negative. So I'll go to y equals and I'll type in my second derivative. Alrighty, and I'll go to my table and type in -7, 0, 4, and I get positive, negative, negative. That's what y'all got? Or do I do that wrong? No, I think that's right. No? What'd you get, Nadine?
I was wondering what you were doing, but I'm sure.
All right, has anyone else done it on Zoom?
Got positive, negative.
I got positive, negative, negative.
Okay, we'll go with it. Positive, negative, negative. This is second derivative, so it's concave up, concave down, concave down. And so for concave up, that happens from -infinity to -6. Concave down, that goes from -6 to 3, and then again from 3 to infinity. So you can't do -6 to infinity because it can't go concave down through a vertical asymptote. And it does look like the concavity changed on both sides of the -6, so it is an inflection point. So we have an inflection point happening at -6 something. To find out what the y value is for that, we put it back into the original function up here. So I'm going to just type it on my calculator. So I have -6 times -6. Enter, divided by -6 minus 3 to the second power. And math frac 4/9. Okay. So we answered everything we could, all 13 little questions with the original function, the first derivative, the second derivative, and all that good stuff. Now we want to graph the function. So this is where on the online homework, it's a little easier because they'll give you a multiple choice thing of graphing, like which one is it? But we're gonna go ahead and do it by hand in case you choose to do the extra credit assignment, then you'll be graphing by hand, which it's really not that bad. So when you go to graph by hand, key points to begin graphing with is if there's any holes, x-intercepts, y-intercepts, asymptotes, max, mins, and inflection points. Those are all dotted lines or points or something specific. Okay. You can kind of just glance at the numbers to see where we should be putting our tick marks on these. For the y-axis, it looks like we just need like maybe 2 tick marks going on. And for the x-axis, the smallest we have is -6, so I'll go out to -6. Maybe I'll go out to -7. All right, so there's no holes to worry about. We have x-intercept and y-intercept are both at 0, 0 there. Horizontal asymptote at y equals 0. So that is a dotted line. Horizontal asymptotes you can only cross once as long as it's not at the far extremes. And that once is going to be where that intercept is right there. Vertical asymptote at 3. Vertical asymptotes you can never cross, not even once. Maximum, there's a maximum at the point -3, 1/2. And there's an inflection point, that's where it changes concavity, at -6, 2, 3, 4, 5, 6, and 4/9, which is a little bit less than, what is 4? 0.4444, so a little less than half. So I'll say right there. All right. So I put all of my points in my asymptotes and stuff. Now I want to see where it's increasing and decreasing and where my concavity is changing. So looking at my increasing, decreasing, it's increasing right here. It's increasing from -infinity to -3. So corresponding to my graph, I'm just going to put a little dotted line here. I'm going to make myself sketch marks down here. I'm increasing till -3. And then I'm increasing again from 3 on to infinity. Then it's decreasing between -3 and 3. So I'm just making myself sketch marks at the bottom. I'll put it together in a second. Then we have its concave up from -infinity to -6. So concave up till about right there. Then it's concave down from -6 to 3 and from 3 to infinity. So this is my scratch work. Putting this together up here, I'm going to do the right side of the asymptote first because that'll be easier because I have an asymptote, a vertical asymptote there and a horizontal asymptote at 0. I can't cross those. I need to be increasing and concave down. So it's just going to be right here. On the left side of the asymptote, starting on the far left over here, I have a horizontal asymptote at 0. So right here, I'm already crossing it once right in the middle, so I don't want to cross it twice. So I'm going to start right above it. I'm going to be increasing and concave up until I hit that point, which is at -6. And then you can even label the point if you're a bad drawer and think I won't notice. And now I'm going to increase up to this maximum and try to change to concave down right there. I'm going to decrease, but stay concave down and go through this point. And then I'm going to keep decreasing concave down and stop before I go through the asymptote. Okay. So again, if you're doing the online stuff, it'll be a multiple choice for which of these graphs is the correct graph. And, you'll be able to figure it out based upon all your items you just found. But on the extra credit thing, you'll have to draw your graph yourself. So, questions on this one? I know that was fun, wasn't it?
Yeah, the drawing of the curves always messes me up. Concave up, concave down.
Yeah.
You said on the that it's choice.
Try that again, Aaron.
Test, it's going to be multiple choice for the graph, like when
Yes, the
when
test.
we're making the graph.
The test is multiple choice for the graph part. Yes.
Okay, thank you.
Uh-huh. All right. So here, this is 4.4.19. This is also from the online homework stuff. So it's also multiple choice. It gives you like 4 choices of graphs, which makes it a pretty easy problem. But for the sake of practicing it for, in case you're doing the extra credit thing, we're going to graph this whole thing. And then I'm going to show you, since it's multiple choice, a very quick way to find the answer if you're not doing the extra credit and you're just doing the online stuff. So on these, I'm going to start at the bottom down here. It says a vertical asymptote at 1, horizontal asymptote at 1 also. So at 1, we have a vertical asymptote. And at y equals 1, we have a horizontal asymptote. All right. Back at the top, it tells us the domain except x equals 1. Nothing to do about that. Great. Here, this line gives us a bunch of points. F of -1 equals 2 means when x is -1, y equals 2. So there's a point right there at -1, 2. F of 0 equals 3 means when x is 0, y is 3. F of 2 equals -1, so when x is 2, y is -1. And f of 3 equals 0. So when x is 3, y is 0. So those were points. This next one is the first derivative. First derivative, all we care about is positive or negative. First derivative tells us where our function is increasing or decreasing. So since it says the first derivative is greater than 0, that means it's positive. So that means our function is increasing on the interval from -infinity to 1. So I'm just going to do a rough sketch down here. And then again from 1 to infinity. So I'll just do a rough sketch down here. So basically it's not decreasing anywhere. Second derivative tells us where our original function is concave up and down. If the second derivative is greater than 0, that means it's positive. So it's concave up from -infinity to 1. Second derivative is less than 0, means it's concave down from 1 to infinity. So putting this together, I'm going to do the left side of the vertical asymptote first. I need to be increasing concave up, not go through my asymptotes, but do go through the points. So it's going to be right here. On the right side of the vertical asymptote, I need to be increasing concave down, not go through the asymptotes, but do go through the points. So it'll be right here. All right. So then let me just kind of, tell you the cheapful way of doing it on your online stuff. On your online stuff, you'll be given a problem like this, and you'll be given a choice of 4 different graphs. Really, if you just go straight to the increasing, decreasing line, find where the first derivative is and look, where is it increasing? Where is it decreasing? You could rule out 3 of the 4 options just from where it's increasing and decreasing.
Wait, I don't get it. Can you repeat that?
Yeah, so on the online homework quizzes and stuff, it's gonna have this problem or one like it and give you 4 choices of graphs. And it'll have one graph that's doing something like this, and one that's doing something like this, and then this, and so forth. And so if you just jump straight to see where is it increasing, where is it decreasing, this one happened to be increasing everywhere except for the asymptote. So we could rule out that one because it's decreasing right there. We could rule out that one because it's decreasing on both sides, and that's the only one left. So it has to be it. You can take advantage of your multiple choice skills here. All right. One more problem. This is from your online homework. It doesn't ask you to do every single thing. No, it does. I'm just kidding. But it'll give you the multiple choice for the graph. But we're going to actually graph it because this will help you with if you're going to do the extra credit stuff. Also, there's a little trick to know in the middle of this problem that's going to save you a ton of time. All right. So, and this is like true for 4.4.73 and like the 2 or 3 before. So if you were given 71, 7 or 70, 71, 72, 74, 75, any of the problems around 7.3, they're all kind of alike. The domain, I'm going to come back to that. That's where my denominator equals 0. And I don't want to do that yet because the first things I always want to do are my y-intercept and horizontal asymptote. On the y-intercept, that's where I plug in x equals 0 for all my x values. So if you just visualize 0 in for your x values, you're left with negative 54 over negative 54, which is 1. So we have a y-intercept at 1. Okay. So it might just ask you to type in 1. It might ask you to type it in as a point. Just gotta pay attention there. I personally like to write points, but do what the online homework is asking, obviously. Horizontal asymptote, that's the Bobo Botten eats RC saying. So our highest exponent on top is 2. Highest exponent on bottom is 2. That's exponents are the same. So we're going to reduce the coefficients in front, which would be 5 over 1. So we have a horizontal asymptote at y equals 5. Okay. Just jumping ahead, I see it says oblique asymptote. Go ahead and put none by that one because it will always be none for our class.
What is oblique asymptote?
Oh, that's where like the numerator has an exponent 1 higher than the bottom and you do long division. It's awful. All right. So these other ones, what we want to do is factor. So that's where I'll go next. On the bottom, x squared is x and x. Factors of 54 1 and 54, 2 and, well, I don't know, 27. Could be some other stuff, but I know 6 and 9. And 6 and 9 will also could add or subtract to give you -3. So I'm going to do a -9 and a +6. On top, factors of 5x squared could only be 5x and x. The factors of 54 could be 1 and 54, 2 and 27, or 6 and 9. Now, there's a really good chance it's going to be either x minus 9 or x plus 6 off to the side, so they cancel. So what I personally would do is just plug them in without any signs and then FOIL it out to see if it would work. So when you FOIL, you'd get 5x squared, and then you'd get 5x times 6, which is 30x, and then 9 times x, which is 9x, and then 9 times 6 is 54. So then the question is 30 and 9, anything you can do with that to make it 21? Yeah, you could do a +30, which would be a positive sign right here, and a -9, which would be a negative right there. All right. So we factored. Before I start canceling and stuff now, I'm going to look at my denominator and see what would cause it to be 0, because I have to still state what my domain is. And so this one, if x minus 9 were 0, that means x is 9. So x cannot be 9. And this one, if x plus 6 were 0, that means x would be -6. So x cannot be -6. All right. Once we factor, we want to cancel. Whatever we cancel is going to be a whole. So even though it didn't ask for a whole, we're going to give it one. So wherever x plus 6 equals 0, there's going to be a whole there. So we have a whole at -6 something. And our simplified version of this function is now 5x minus 9 over x minus 9. And to find the y value for the whole, you put the x back in the simplified version. So I have 5 times -6 minus 9 over -6 minus 9. Gives me -39 over -15, which is 13 over 5. So it didn't ask for a whole, but I wrote it there anyway. And then what I personally would do is put stars all around your scratch work, because people forget to put that hole on their number line. If you forget to put that hole on your number line, then your intervals for increasing, decreasing, concave up, down, all that will be wrong. So don't forget about the hole. All right. Whatever's left in the numerator, if we set that equal to 0, we get our x-intercept. So I'm going to add 9 to the other side, divide both sides by 5, and I get x equals 9/5. Whatever's left in the denominator, that's going to be our vertical asymptote. And we get x equals 9. So all those things we just found are found without doing any calculus. That was all algebra. To find this next group of items, we're going to need to do the first derivative test. Now here's my huge hint for you. When you go to take the first derivative, do not take the first derivative of that big awful equation it gave you in the beginning. You can take the derivative of your simplified version and everything will still work out perfectly. And it's a lot easier to take the derivative of the simplified version. All right, so taking my derivative, I'm going to do low d high. Low, just write it down. D high, derivative of the high is 5. Minus high. D low, derivative of the low is 1. Over the square of what's below. Looking on both sides of my negative sign, there's nothing I can even pull out from both sides. So I'll just go ahead and distribute here. Distribute that negative sign also. And my 5x's will cancel. And so I end up with my first derivative equals negative 36 over x minus 9 squared. All right. So I want to look at 2 places. I want to know, where does my derivative equal 0 and where does my derivative not exist? This will produce critical values for me. My derivative is going to equal 0 wherever my numerator equals 0. But negative 36 can never equal 0. So that doesn't give me anything. My derivative does not exist wherever my denominator equals 0. And you only have to do what's in the parentheses. And I get x equals 9. And then I ask myself, is that a critical value? No, it's not, because my domain said that x cannot be 9. So it's not a critical value. So I checked the 2 places that could give me critical values and I didn't get any. So that means there are no critical values. And if there's no critical values, what else do you know?
No min and max.
That's right. There's no max or min, because critical value is the only place those could happen. But for increasing, decreasing, we still need to put 9 on our number line because it appeared, it's important. And we also need to put the thing, we put stars all around up there at the top, the hole. So any holes, any vertical asymptotes go on the number line. But neither one of these are critical values. So if you need to put not a critical value beside them both, just so you remember these are not going to be maxes or mins, then you should do that. Picking numbers to the left and right, I'm going to test each of these in the first derivative. And the only thing I care about is, does it come out to be positive or negative? So you can use your table on your calculator if you want to. However, if you look at our first derivative here, negative 36 is never going to not be negative, no matter what number we put in. And on bottom, no matter what number we put in, we're going to square it, which is always going to make it positive. So no matter what number we put in, we have a negative over a positive, which will always give us a negative. But if that didn't make sense to you, then by all means use your table. So it's increasing never. So I'm just going to write nowhere. But what you don't want to do, you don't want to say it's decreasing from negative infinity to infinity, because it's not decreasing through the hole and it's not decreasing through the vertical asymptote. It's decreasing from negative infinity to negative 6. and then again from -6 to 9, and then again from 9 to infinity. All right. For these next three items, we're going to use the second derivative. Now, if you look at our first derivative right here, it does not have an x in the numerator. It's just a number. So before I take the second derivative, I would totally bring that denominator to the top. If there's not an x in the numerator, then there's no need to use the quotient rule. Unless you really wanted to, then go for it. So taking the second derivative, we have -36 stuff to the -2. Derivative will be -2 times -36, which is 72, stuff to the -3. Copy paste the stuff in the parentheses, times the derivative of the stuff, which is just times 1. And then I'm going to rewrite this with no negative exponents, so we can work with it. So 72 over x minus 9 cubed. Now I want to know where the second derivative equals 0 and where the second derivative does not exist. It's going to equal 0 wherever the numerator equals 0. But 72 is never going to equal 0. So that does not give us any possible inflection points. It's going to not exist wherever the denominator equals 0, which is when x minus 9 equals 0, so at x equals 9. But then you ask yourself, is that a possible inflection point? No, 9 is not in the domain, so it is not an inflection point. So we checked both places of where we could possibly have an inflection point and came up with nothing. So there are no inflection points. But that does not mean concavity is not changing. Concavity can be changing around holes or asymptotes. So I'm going to make my number line. And I'm going to put the hole on it and the asymptote on it. And if you need to make yourself a little note, not an inflection point, then that could be useful. Picking numbers to the left and right, I'd pick like -7, 0, and 10. And I want to plug these into my second derivative. And all I care about is, do they come out to be positive or negative? Positive or negative? So you can use your table to do this if you would like. You can just do it by hand if you would like. It doesn't matter. Doing it by hand, I would have a positive in the numerator each time. -16 cubed is still negative, so this will be negative. And this one will be negative, and this one will be positive. So I have concave down, concave up. So it's concave up from 9 to infinity. It's concave down from -infinity to -6. And then again from -6 to 9. So look at this, even though it looks like there was an inflection point at 9, there was not, okay? The concavity changed on both sides of a vertical asymptote. That was not an inflection point, so don't confuse yourself when that happens. Now I'm erasing myself a spot in the middle here so I can graph this function.
So we plug in the hole, like the x value of the hole, And anytime we do a derivative test, whether that's the first derivative test or the second.
Yes, holes and vertical asymptotes are always tested. All right. So putting this all together, important things to plot would be holes, intercepts, asymptotes, max, mins, and inflection points. Well, there are no max, mins, and inflection points. We do have a hole and some intercepts and stuff, and I'm just kind of glancing at my numbers to see how to make my tick marks. I see -6, 13/5 is a little less than 3, 5, 9. All right, so I'm gonna go out 10. All right, and then up and down is usually more spread out. I say usually. I'm going to add some in there. All right. So starting with the hole, there's a hole at -6 and 13/5. So just to kind of see where 13/5 is. That is not a 13, so don't look at that. 2.6. So -6 and about 2.6, there's a hole about right there. An x-intercept at 9/5, which is, did I not do that? I don't know.
We just did 13/5.
That's right. It's been a long day. All right, 9/5 is 1.8. So 1.8. Oh, x-intercept, my bad. Nothing wrong with me. 1.8 is my x-intercept. And then my y-intercept is at 1. All right. Then I have a horizontal asymptote at 5. That's an imaginary line that I might could cross once if it's in the middle. And then a vertical asymptote at 9. That is an imaginary line we do not cross. All right, well, those are the important points. So now I'm looking for increasing, decreasing. So if we look down here, it's never increasing. It will be decreasing the whole time except for it doesn't decrease through the hole or the asymptote. So it's basically decreasing to the hole and then decreasing to the asymptote and then decreasing some more. For concavity, it's concave up from 9 to infinity. So way over here on this side, it's going to be concave up. But then it's concave down until we reach the hole, and it's concave down after the hole. So putting this together, I'm going to do on the right side of the vertical asymptote first. On the right side of the vertical asymptote, I need to be decreasing concave up and not go through either asymptote. So it's going to have to be way up here if I don't want to go through either asymptote. A lot of people will try to put this one like down here like that. Okay, but look, when you draw your arrow, that implies you're going to go straight up through that asymptote. You don't want to do that. On the left side, I need to be decreasing the entire time, concave down the entire time, not go through either asymptote, but I do need to go through, quote unquote, the whole and both points. So again, on the extra credit thing, you would be graphing this by hand like we just did, but on the online homework, online quizzes and stuff, you would have 4 multiple choice problems or guesses on it, and you could probably figure it out just by the increasing, decreasing part of the problem. Okay. Alrighty. So you have, let me stop recording a second.